In our last video, we dove deep into the ICS-43434 digital I2S microphone. We explored its PCB module pinout and schematic, understood important microphone terminologies, walked through the data sheet, and wrapped up with a comparison of other digital MEMS microphones available in the market. In today's video, we will take a step further, go through the wiring diagram, work with the new updated I2S APIs in ESP-IDF. We will add a UART section helpful in transmitting the I2S audio data serially. And finally, there would be some math waiting for us too. Namaste and welcome back to Avinashee Tech. The connection is pretty straightforward. You just need to remember which function each pin of the microphone is responsible for. Also keep in mind that different PCB modules sometimes use different naming conventions for the same pins. First, connect the VDD pin of the ICS-43434 to the 3V3 power pin of the ESP32 and the ground pin to ground. Next, connect the BCLK or SCK pin, which is the main serial clock, to GPIO 14 of the ESP32. The LRCL or WS pin, which is the word select or sample rate clock, goes to GPIO 22. Now connect the SD or Dout pin, which carries the audio data, to GPIO 21 of the ESP32. The LR or SEL pin is connected to ground, making this configuration a mono left channel setup. For the UART part, connect the RX pin of the USB TTL module to the TX pin or GPIO 17 of the ESP32 and connect ground to ground as usual. That's it. Pretty simple, right? Before we move ahead, let's hit the warning button. This video is for engineering nerds. If you're one, get comfortable in your seat. If not, you might want to exit here. Alright, I'm inside VS Code with our new ESP-IDF project. You will see two files here, I2S.h and I2S.c. These handle all our I2S operations. Now, if you have worked with I2S examples online, you will notice that most of them still use the legacy driver by including the old I2S.h header. But if you check the official Espressif documentation, it clearly states that the legacy driver may be removed in the future. Here's what has changed internally. The HAL layer at the bottom is still untouched, but the upper layer or the driver layer has been completely updated with new APIs and new header files depending on the digital audio format you are using. In our case, we are using the standard I2S format, not PDM or TDM. So we will be working with I2S std.h. Back in our project's I2S.h file, we have included I2S std.h along with the GPIO header. Next, we define some basic macros. We have chosen a sample rate of 16 kHz as discussed in the previous video. Along with that, we have defined a buffer size of 512 samples. And don't worry, we will break down what this 512 actually means in a moment. Below that, we define the I2S pin configuration exactly as discussed in the wiring section. Apart from this, we also have two function declarations. That's it for the I2S.h header file. Now, let's take a look at the I2S.c source file. Since we are using the standard I2S driver with the new updated API, the first thing we do is configure it. For that, we create a standard configuration structure called stdcfg and start initializing its members. The first member is the clock configuration structure, and here we use the default configuration for our selected sample rate of 16 kHz. Next, we configure the slot configuration structure. This structure has several important members. The first one is data bit width, which represents the number of valid data bits per sample. Then we have slot bit width, which represents the total number of bits per slot, left or right. We again set this to 32 bits because that's what the microphone actually transmits after padding. Next, we set the slot mode to mono and the slot mask to the left slot. After that, we configure WS width, which defines how many bit clock cycles the WS signal stays high. This is set to 32 clock cycles, which matches the number of bits in each slot. Then comes WS fall, which controls polarity of the WS signal. We set this to false or 0, so that the left channel is enabled first. As discussed in the previous video, the WS signal changes one clock cycle before the MSB of the serial data. This behavior corresponds to Philips I2S mode, and we enable that by setting bit shift to true. Finally, we configure the GPIO pin structure where we assign BCLK, WS, and DIN pins of the ESP32 I2S peripheral. These are mapped to the pin definitions we already created in our header file. The new I2S driver works in three different levels: platform, controller, and channel. The platform level manages resources for all I2S controllers in the chip. The controller level refers to a specific hardware block, either I2S 0 or I2S 1. And the channel level handles whether a particular peripheral instance is being used for transmit or receive. So in our code, the RX handle is the I2S channel handle specifically meant for receiving data. Next, we have the I2S setup function. Inside this, we start by creating another structure variable called CHAN-CFG, which is responsible for channel configuration. The first member we configure is the port ID, and we set it to I2S 0. Next, we set the role to master. After that, we configure the DMA parameters. The first DMA parameter is the number of DMA descriptors, which we have set to 8. The second one is the number of frame samples per DMA buffer, which we have set to 120. Now, let's take a step back and understand how these values are chosen. The I2S peripheral triggers the DMA controller to transfer data from the peripheral directly into SRAM without CPU intervention. Before this transfer can begin, CPU must initialize the DMA controller with important parameters: how much data to transfer, where the peripheral register lives, and which memory area in SRAM should receive the data. The DMA buffer size is calculated using this formula: DMA frame num multiplied by slot num multiplied by bit width divided by 8. For our left channel mono setup, slot num equals 1. So our buffer size becomes 120 into 32 by 8, which is equal to 480 bytes. Now let's take a look at what a DMA descriptor actually is. A DMA descriptor is like a linked list node in memory, and it is 3 words long, where a word stands for 32 bits. The first word contains control fields: an owner bit, which tells whether the CPU or DMA currently owns the buffer; an EOF or end of frame field, which indicates whether this is the last descriptor in the chain; a length field, which specifies the number of valid bytes in the buffer; a size field, which specifies the total allocated buffer size. In our case, since the microphone has 24 valid bits and it is padded into 32-bit slots, both the length and size usually end up being the same, because the padded bits are still physically transferred over the bus. The second word of the descriptor is the buffer address pointer. It points to the actual data buffer. The third word is the pointer to the next DMA descriptor, which creates the linked list behavior. So if we have 8 descriptors, each pointing to a 480 byte buffer, then the total audio buffer memory in SRAM is 480 cross 8 equals to 3840 bytes. And the descriptors themselves occupy 12 bytes cross 8 equivalent to 96 bytes. Now the beautiful part, how it runs in real time. While the CPU is reading buffer 1, DMA can fill buffer 2. When buffer 2 gets filled, an interrupt is raised. CPU moves to buffer 2, DMA moves to buffer 3. This continues in a circular fashion. So after buffer 4 is filled, DMA goes back to buffer 1. Now, this doesn't mean CPU and DMA access memory at the exact same instant. They both share the same system bus, and the chip uses hardware bus arbitration to give each one a time window to complete its operation without collisions. Next in the sequence, we call the I2S new channel function to allocate a new I2S channel. Here we pass the CHAN-CFG structure by reference. We set the TX channel handle to null and pass the RX handle by reference, because in this project, we only care about receiving audio data. After that, we call I2S channel init std mode. In this function, we pass the RX channel handle along with the std-cfg structure by reference to initialize the channel in standard I2S mode. Finally, we call the I2S channel enable function. This is the point where the hardware clocks are enabled and the I2S peripheral actually starts running. Inside the I2S read samples function, we call I2S channel read to fetch the I2S audio data. The arguments we pass are the RX channel handle, a pointer to the application data buffer, the maximum size of that buffer, a variable to store the number of bytes actually read, and finally the timeout value, which we set to port max delay. This means the function will block execution until it has read enough I2S data to completely fill the application buffer. For UART support, we have added a new UART.h header file where we define the TX and RX pin mappings along with the required function declarations. Inside UART.c, we implement the function definitions. We create a UART config structure and initialize it with our UART parameters. Baud rate is set to 921.600 and the rest of the fields are kept at their default values. After that, we install the UART driver, configure the parameters, and assign the pins. And that gets our serial communication ready. To actually transmit data, we use a simple send data wrapper function, which internally calls the UART write bytes function. Alright, now let's jump to the main source file. Here, we start our main function by initializing both I2S and UART. Inside the infinite while loop, we first call the read samples function and pass in our application buffer rbuff. Next, we send the I2S data stream over UART by calling the send data function in blocking mode. Simple, right? Okay, now let me introduce you to some equations for more clarity on the topic. Let's list out the values we already know. Our sample rate is 16 kHz. Data bit width is 32 bits. Slot num is 1. Now if we put these values into the DMA buffer size equation, the only variable left is DMA frame num. On ESP32, this value for slot num 1 can go up to 1023 samples, and we have chosen 120, which is safely within the limit. Now let's talk about the interrupt interval. At a 16 kHz frame rate, one WS sample period is 1 by 16,000 equals 62.5 microseconds. So for 120 samples, the total time to fill one DMA buffer would be 120 multiplied by 62.5 microseconds equivalent to 7.5 milliseconds. That means the DMA will raise an interrupt every 7.5 milliseconds. So that is our interrupt interval. Next, we have 8 DMA descriptors, and each DMA buffer is 480 bytes. So the total DMA memory becomes 8 cross 480 equivalent to 3840 bytes. This means that if we want to drain all DMA buffers in a single call to I2S channel read, the application receive buffer must be larger than 3840 bytes. However, this is not mandatory. In most streaming use cases, we do not read all DMA buffers at once. Instead, we read a smaller chunk of data more frequently. This helps in saving RAM, reducing end-to-end latency. In our use case, the audio data is immediately transmitted over UART, so it makes sense to keep the application buffer smaller and stream continuously. Therefore, we chose 512 samples per read, which corresponds to 2048 bytes. This buffer size is sufficient for our application, while the DMA descriptors handle any timing jitter in the background. So until 512 samples are accumulated, code will block inside the while loop. The time required to collect 512 samples at 16 kHz sample rate is close to 32 milliseconds. After that, UART kicks in and we are transmitting 512 samples, so that is 2048 bytes per chunk. So at a baud rate of 921.600 and including the start and stop bit, this takes roughly 22 milliseconds. Now when we add timing code, flash it and monitor it on the serial monitor, we observe a polling time of about 59 milliseconds. And if we divide this observed polling time by the interrupt interval, we get 7.86. And the next integer greater than this value is 8, which perfectly matches our DMA descriptor count. I know this part can feel a bit confusing, so feel free to watch it again if it didn't click the first time. If you have tried different polling timings in your own projects, share your results in the comments. Alright, that's it. I rest my case. So in this video, we covered the connection diagram, a full code walkthrough, and even a mathematical breakdown of how the parameters work. I've tried my best to keep everything clear and accurate. But if you have more insights on this topic, feel free to share them in the comments. If you haven't watched the previous video in this series, where we discuss the PCB module pinout schematic and the microphone data sheet, I highly recommend checking that out. It will help you understand this tiny microphone much better. And don't forget to subscribe to the channel, because in the next video, we will build a Python script to record audio on the PC. And after that, we will try some real-world recording and playback experiments with this microphone for some proper engineering fun. If you enjoyed the content, make sure to like and share this video. This is Avinashee Tech, over and out.